Maybe we can start. The time is up now. Hello everyone. Today we will discuss another paper on fusion of the images for the self-driving project. If I remember correctly, in the very beginning of this course, we have another paper on this kind of fusion project for self-driving one. I think I presented Xinghao Xiang one. And today we'll have another paper on a similar project. However, this paper is from Google, and they try to analyze the data from Waymo. Waymo actually is a company, it's a small company purchased by Google many years ago, and Waymo is focused on self-driving for many years. So they also release self-driving, this kind of data set to the public. They also create some like open challenges to the public to compete. I mean, with some awards. So today the paper is on the fusion, and there's also discussed alignment between the 2D camera image and the 3D point cloud image as well. And the presenter today will be Barry Singh, and Barry will help us lead the discussion for this paper, and we can give the time to Barry. You can start when you're ready, Barry.
All right, thank you so much. So welcome to our paper is Deep Fusion, Lidar-Camera Deep Fusion for multi-modal 3D object detection. So let's start with some backgrounds. So first, like we had some papers about graph neural networks, and then we had some papers about recommender systems. So this is time to go back to the vision part. And I just want to go over the challenges of 3D vision and 2D vision, how they relate to each other, what the challenges are, and then what like this paper is trying to accomplish in 3D vision. So in 2D vision, our input has two dimensions. It has height and weight. And if we say, for example, let's say like 1,000 by 1,000, then we have like 1,000,000 images. And 1,000,000 images is a couple megabytes, so we can like definitely store it easily in modern computers. And then this representation also makes it possible to use very efficient and successful neural networks. These can be convolutional neural networks or transformers. We have seen quite a lot of accomplishments of both of these, and they're just like currently every day we see one convolutional neural network outperforming another transformer, and that transformer outperforming a convolutional neural network. And the advantage of the images in 2D is that there is very dense information in images. So an image, every pixel brings a value. Even if it's a background, we know that it's a background, so we have a very dense information. However, when we move to 3D, then like naively, if you want to represent the same, like using the same method, then our dimensionality would be height times weight times the dimensionality. And then if it's like 1,000 by 1,000 by 1,000, then the number of numbers we need to represent an image directly goes to like billions, which would correspond to like a gigabyte. So if we wanna, for example, represent like I don't know, like a batch of 16 scenes, then we would need like 16 gigabytes of memory just to store the scene. And then this definitely is not possible with the current machine. So there are definitely things like this is definitely one of the major points in 3D vision that researchers are trying to address. And then there are some things that we can utilize in 3D vision. So I said that in 2D vision, we have like very dense information. However, when we move to 3D vision, we have a very sparse information in 3D. So imagine that we represent the whole, for example, an indoor scene, a room as a grid. And this grid has a lot of air. So many numbers is gonna be zero in this whole, like the tensor of the image. So we can utilize this feature to maybe efficiently encode the 3D structure. And we know that like we only need the surfaces actually to represent the 3D. We don't need the air. We also don't need any information about the inside of the objects. So let's see how we can use the nature of 3D to represent our input. So I'm gonna go over some of the most common input representation methods for 3D that utilize some 3D, like the nature of 3D to best make use of the information and then just like increase efficiency. So these are volumetric grids, point clouds, polygon meshes, and implicit representation. So let's go over them one by one to see how they can be used and then what are the advantages and disadvantages of these methods. So we first start with volumetric grids. So a volumetric grid is just a grid of 3D pixels. And then the 3D pixels are called voxels. So for example, if we have like this grid with this rabbit here, then it can be like dimensionality of this can be like 32 by 32 by 32. So we can have any kind of an image, and then we can just like put we have the input representation in any kind, and then we just put this grid on top of this representation, and then for each voxel we just check what kind of an information this input representation has in this voxel, and then we decide if it's a surface or not and so forth. So this is called voxelization. We convert any kind of input to voxels. And since I mentioned that, just like I mentioned before, we need to have a low dimensionality. We cannot go to like thousands because it would mean like it would cause like gigabytes of data. So we usually keep in like small dimensionality, which is like 30 by 30 by 30. We can go up to maybe like 100, but like more than 100 with just this naive method doesn't work quite well on the GPUs. So one of the biggest advantages of volumetric grids is that they are very suitable for 3D convolutions. So we already know the power of 2D convolutions in images, so we can efficiently apply 3D convolutions to these volumetric grids and then just like do any kind of a task on the input image. So on the bottom, we have one of the most famous architectures that use volumetric grids. So this is 3D CNN. So let's have a look how they utilize 3D volumetric grids. So as we can see on the left-hand side, this has an input of 30 by 30 by 30. So this is like an object. And then we do some 3D convolutions on this image on this tensor to get like a feature of dimension 30 by 30. And then we then do some like multi-layer perceptrons to just go to our like final feature dimensionality, which is 40, and then using some softmax, we can do object classification. So 3D convolutions and then MLP, very simple, but a very effective method. So this was one of the best methods in 2016. So however, we know that like the dimensionality of the images is always gonna be low. So how can we circumvent this? So researchers found out that we can utilize the nature of 3D, and especially the feature that we only have information in the surface. We don't have information anywhere but the surface. So what about applying these convolutions only in the surface of the image? Not like we don't want to just like diffuse these features to the whole grid, but we always keep around the around the edges, around the borders of the objects. So we utilize this feature. And then there is also another observation that if resolution increases, actually the amount of empty space in the grid increases as well. And so we can see this in these two pictures. On the left-hand side, we have 4 chairs, and all chairs are represented by volumetric grids of different resolutions. On the left-hand side, 13% of the whole grid is occupied. But when we increase the density, increase the resolution, then the space that the surface takes gets smaller. And because it gets smaller, it gets more fine. Then on the right-hand side, for example, we have 128 to the power of 3 dimensionality, and then only 2.3% of the whole grid is occupied. So if we concentrate our convolutions into only this 2% of the image, then it gets way more efficient. Also, then we don't need to keep a 100, for example, for this 128 by 128 by 128 metrics, but we can just encode the 2% of all the values in, for example, an efficient hash map, where we have often just like retrieval. So this hash map would store it, and then we apply our convolutions using the retrieval functions of the hash map. And on the right-hand side, we see like a convolution kernel. So this red kernel goes all the way around this occupied pixels, but then it doesn't go anywhere else in the image. So let's have one question. So this question is, which type of convolution do you think is faster when the number of computations we are going to perform is the same? So A, regular convolutions, B, sparse convolutions. So what about, like, if you have an idea, please just write something to the chat and see if we come to like any results. What do you think? Regular convolutions or sparse convolutions? Which one would be faster if the number of computations is the same? This is a little tricky question, so I would love to see some answers in the chat. Just guesses. Like, it's not a big deal. All right. So we have a couple answers as sparse convolutions. So that's also like immediately what I thought about. But I thought, like, sparse convolutions, okay, like we don't need to do so many operations. It's gonna be way faster. But it turns out that regular convolutions are actually faster. But the trick is here that the number of computations is the same. So what happens in regular convolutions is that we have a dimensionality of 32 by 32 by 32. And then we have, for example, we do all the sequential memory access operations. So if we apply the convolution, we don't need to check the location of the next cell in the memory. We just go to the next cell in the memory without any like hash map operations, which is significantly more efficient. So if the number of computations is the same, then sparse, like regular convolutions, are faster. When we do sparse convolutions, then we need to, in every step, we need to just do a get operation in the hash map, and then the hash map does this random access memory, which results in usually in slower time. So when we do sparse convolutions, we can fit a higher resolution object into our memory. However, we sacrifice in especially the running time of the whole method. So if you ever use sparse convolutions in our methods, then we should know that it's going to be slower than using this regular convolution, even though we win by a lot using sparse convolutions and sparsity. All right, let's move on to point clouds. So point clouds, it's probably one of the most famous representations. And this is just a point cloud is just an unstructured set of points. So we have n points, and each point have x, y, z values. So these are required. And then it can also have like additional values such as like alpha value, RGB value, and then any values that we know from like computer graphics, for example, like how shiny this surface is, maybe just like how soft the surface is, so many things. Just like this, an unstructured set of points, x, y, z coordinates with some additional features. So because it's an unstructured set, the spatial information is very hard to capture. So for example, if we have an image, we know exactly, very easy, what the neighboring pixels are. Go to this array and then move right or up or left, and then you're gonna land in the neighbor pixels. However, it's very challenging in point clouds because we don't know what the neighboring objects are. It's just a long list of points. So for neighbor retrieval, we need to do some like nearest neighbor search, which is significantly more costlier than doing these operations in images. Also, the notion of surface is unclear. So if you have all these points, it's a little non-trivial to generate the surfaces. So just because the 2 points like are close to each other, we don't know how the surface needs to be created. There are definitely methods that do it, but this is not a trivial solution. Also,
I have a question regarding this. I mean, isn't there any depth information with this? Because isn't it the same technology that there is an iPhone,
exactly, yeah.
Unlock? So there must be some depth information in this point cloud.
Exactly. We have better than actually the depth. We have x, y, z coordinates of each point.
Okay. So
however,
so why isn't the surface clear then? Because if we have the depth information of every.
Exactly. So we know that a point is on the surface, but when we want to draw this whole surface, for example, we have all the points, for example, around this rabbit that we saw like up here, for example, the volumetric grid rabbit. So if we have this rabbit, then we have all the points on it, but we don't know actually like how to draw this rabbit using these points. We need to somehow like create surfaces by just like drawing some surfaces using the points. Maybe we can use as like triangulation of the points. There are several methods. We can just like triangulate between the points to generate the surface, but the surface as it is not like trivial. We need to apply some algorithms to get a point out, get a surface out of it, and then it's also not unique, like not a unique result can be retrieved by it.
Okay, so you mean there's some problem? I mean, clustering those points is hard. Clustering those points such that we find a surface is hard. Is that what you
said? Yeah. So not that, like for example, when you look at the dolphin as the polygon mesh, like we need to, if we have a point cloud for this dolphin, we need to somehow have this polygon mesh. We need to convert this, for example, to a polygon so that we know where the surfaces are. We know, for example, at some point, like how can we get the surface normal? For example, how can we get the surface normal for the point cloud of a dolphin? We can't find it because we don't know the surface. Like we don't know what the direction of the surface is, and then how it's curved, because we only have single points. So we somehow need to draw edges between those points, and then those edges would build, for example, different surfaces, and then we can get the normal of the surface, which would be one of the most common ways of generating a surface out of it, and then just like getting surface normals.
Yeah, thanks.
All right. And one of the major problems is that the point density is not uniform. So if we get a point cloud of a room, then some parts of the room have so many points, and then some parts of the room, for example, a distance point, which are not reachable, don't have a lot of points. And then because we operate on the set of points, then the dense areas have so much effect on the result than the sparse areas, which decreases the accuracy. usually when we want to do like any kind of a segmentation or classification or object detection task. But the biggest advantage of the point clouds is that they're very easy to get using commercial sensors. Even like as our friend just mentioned, just like commercial sensors, like just phones can even get 3D point clouds. We have like Kinect sensors, we have LiDAR cameras, so they're very accessible. The most accessible, actually, the input method when we wanna perform on 3D. And on the bottom of the slide, we see PointNet. This is also one of the most famous 3D architectures, published by the same author, actually, with the previous model. So this model, we can see this also as like an object classification model. So in the start, we have the input points. So the input points are just like m/3, xyz coordinates for m points. And then we have this input transform layer. So this input transform layer is just like an MLP that gives the network the opportunity to map these points into like another, apply any transformation to it. And then it's going to be still m/3, but maybe we reorder the points. Maybe we just shift the points. This can just like act as an augmentation, any kind of it. And then we apply some one-dimensional multi-layer perceptrons on it to just like increase the dimension from 3 to 64. And then we do this transformation layer again, and then we have n/64 points, and then we apply a couple of multi-layer perceptrons to finally get to n/1024 features. So for each point, we have a 1000-dimensional vector, and then we just apply a max pool on it to get the global feature. So this global feature is 1/2024, is passed to some MLPs, and then we get the output scores of all the classes. So this is one of the most important baselines that most of the models use, and this utilizes only point clouds. All right, and this is also, as I briefly mentioned, it's very easy to convert between point clouds and volumetric grids. So if we build a point, if we have a point cloud, we just, for the scene, we built a 3D grid. So we just put an imaginary 3D grid on our scene, and then for each voxel, we check which points are in this voxel. And then we can, for example, average over the features of these points in each voxel, or we can just like sample one of them, or we can do some max pooling, any kind of a pooling operator on each voxel. And then we just have voxelized our point cloud, and it's ready to perform 3D convolutions. And from this voxel grid, we can also convert them to pillars. So a pillar is just reducing the voxel by one dimension. So we average, for example, over the voxels in the same column, and this column is a pillar. So if we average over them, then we convert the voxel grid from 3D to 2D, and then it's ready to perform 2D convolutions. So this pillar method is also one of the baselines that are the paper that we're gonna talk about today uses, which is definitely one of the most successful methods on 3D object detection. And then we go to Polygon Meshes. So Polygon Meshes, as we see this dolphin, this is extremely popular in computer graphics. So this gives us very high quality representation. It's also very efficient to render polygon meshes compared to the other ones, and it's very easy to manipulate. So an artist can just like use one of the 3D tools to drag and drop all these points and edges, and then add edges, remove edges to modify the object as they wish. But they're a little hard to perform, hard to use in machine learning. So it's not a trivial data structure to apply any of the conventional methods. There are some methods that use, for example, graph neural networks on it. So all the edges are the edges of the graph, and then the points are the nodes. and then all of them have features, and then we propagate features to, for example, perform like shape generation or object classification, things like that. But this is definitely one of the non-trivial input representations. For example, when we want to do shape generation, an idea would be to just start with a sphere mesh, just like we want to go to, for example, a dolphin. We start with a sphere mesh, and then we pass it through graph neural networks to eventually refine it in several steps iteratively to land in a specific object, which can be this dolphin. So we can interpret all these objects as a refinement of the sphere mesh, actually. So there are quite interesting works along these lines, but this is not exactly the representation that is used so often. And the last thing I want to mention is the implicit representation. So the implicit representation can be thought as a function that maps each of the coordinates into a scalar value, and then the scalar value simply shows the distance of this point to the nearest surface. So if this scalar value is 0, we know that this point is on a surface. If it's greater than 0, we know that this is outside of all surfaces. And then if it's closer than 0, we know that this is inside of a surface. So this is inside of an object that is not observable to our measurements. And this f can be approximated by a neural network. So if our neural network fits this function for the specific object, then we can just query this neural network to get the points for like all the points. We can get the distance to the surface, and then we can generate our object. This is also one of the methods that there are so many works working on it, but this is not one of the best performing methods, especially in a 3D detection. So now the second question: which input representation model is used in state-of-the-art 3D object detection? So I again want you to just give your guess about which of them is the most common one. You probably also know about them, but I just checked a couple object detection benchmarks to see what is used the most, and just all right, I'm gonna give you 15 minutes to put some answers to the chat. 15 seconds. So we have voxel grids, point clouds, polygon meshes, and implicit representation, which is used in the most common benchmarks as the state-of-the-art. All right, can we get a couple answers? All right, we have point clouds and voxelized grid. So this question does not have a very clear answer. So in most cases, point clouds are used as input, but then they're in most cases converted to voxelized grids, and then people apply some sparse convolutions on them. So point clouds and voxel grid are both valid answers, but the input is usually point clouds. The first initial input is usually the point clouds, because this is how we retrieve 3D data the most efficiently. All right, so let's go to object detection. So our specific problem. So in object detection, our input is voxels or a point cloud, which is usually a point cloud, but we can just convert between them easily. And then our output is 3D bounding boxes. So for each object, we give the 3D bounding box. So the usual steps is just from the input, we extract features, and then we just do object detection part similar to the 2D detectors. So there are some one-stage detectors who just directly map these features, the extracted features, into bounding boxes. And there are two-stage detectors which just get the features and then create proposals, which are also called anchors. and then just refine them in the next stage. So in the first stage, we have the proposals, and in the next stage, we have refinement and filtering, and then we give the predictions. So they usually also, in addition to the 2D detectors, they utilize the features of 3D world, where, for example, if you have a point cloud, like closer points, like it's way easier to cluster in 3D than in 2D, because in 2D, we have all the neighboring pixels, but in 3D, we don't have this neighboring information so easily. We can just, like, in most cases, we can just group all the points together, because usually the objects are like not so close to each other. There, for example, if you have like so many chairs, like we can probably just use a k-nearest neighbor algorithm to just separate all the chairs from each other. So we can utilize the sparsity of the points, sparsity of the voxels. And what kind of evaluation metrics we use? So the most common evaluation matrix is average precision. So this is actually the average precision while recall increases. On the right-hand side, we have the precision versus recall graph. And then this plot says, okay, if we want to reach, for example, 100% recall, then we need to sacrifice a little from precision. But if you want to have low recall, then we can get higher precision. So the average area below this curve is actually what we call as the average precision. So average precision of the bounding boxes when recall increases. Then using this average precision, we can also calculate mean average precision, which is the mean of AP values across all the classes. And our specific data set, way more open data set, also defines average precision heading as an evaluation metric. So this metric just weights AP by the heading angle accuracy. So this heading angle is the angle of the bounding box, because they think that if you predict something, you need to also predict where this object is headed to. So you just weight the average precision by the heading angle accuracy. So if it's accurate, then this precision is more valuable, but it's not. If it's not accurate, then this has less value. This is less accurate, so to say. And then the data set that is used in this work is Waymo Open Data Set. So Waymo Open Data Set has perception and motion data sets. And as a professor mentioned, this has several benchmarks, several challenges, motion prediction challenge, occupancy and flow prediction challenge, 3D object detection challenge, and 3D semantic segmentation challenge. They also just like do this as a like yearly competition. They also started to do some cash prizes on it. So this is just like a nice initiative to make people like make such a good data set available, and then just yeah, make it easy for the scientists to work on 3D data. So now we move to multi-modal vision. So especially in autonomous driving, we know that single model vision is usually not sufficient. So if you only use LiDAR, we may skip so many things. If you only use 2D images, the camera, then we're missing the depth information. But we can merge these most accessible sensors, two of the most accessible sensors in autonomous driving, to perform our tasks. And the problem is LiDAR is in 3D, which outputs a point cloud, and the image is 2D. So the main challenge is, how do we align these features? How can we merge the features extracted from 2D images and 3D images with each other? And we definitely need a successful sensor fusion method to utilize the both input modalities. And we went over these in our previous autonomous driving paper presentation as well. So I'm going to briefly mention the fusion methods. So first, we have geometric fusion, which just uses linear algebra. And then we know all the features of the cameras. We know the features of the LiDAR sensor. You can just map between 2D and 3D. And the other thing is neural fusion. so where we use neural networks to align these features. So when we go to input fusion, we can perform fusion in the very beginning. So we can have all the LiDAR, we can have the LiDAR point cloud, and then we can just add the features that we get from the pixels, concatenate, find the corresponding point in the point cloud, and just put the features to each point in the point cloud, and then pass it to a LiDAR detector. Or we can do the reverse. We can map the point cloud, LiDAR point cloud, into, for example, bird eye view or any kind of view that is similar to the camera. And then we just concatenate, we just find the appropriate pixel in the image, and then we just add this depth information, for example, to the appropriate pixel in the image. So this is called input fusion. Without doing any neural network, we map the input to both the 2D or both the 3D. And then we feed this input to a neural network. In late vision, however, we first extract features from both of the modalities, and then we map features into 2D or 3D and pass it to a neural network. The challenge here is that the feature dimension, so when we extract features, the feature dimensionality is usually lower than the input dimensionality. So each feature corresponds to more than one point, which makes it a little harder to understand, to find a one-to-one mapping between the pixels in the image and the points. And if the feature extractor methods are like different from each other, this gets even harder just using some linear algebra methods. And then the newcomers are the neural fusion methods. So first, we can just like naively concatenate extracted features from both modalities and then pass it to a neural network and just like expect the MLP layers in the end align these features and then generate a useful alignment. Or we can utilize our champion attention to find the correct alignment between the features where we don't use like geometry at all. So these are the fusion methods, and probably everyone guesses which one we're going to present, which is another neural fusion method. But first, let's have a look at what the challenges of the fusion are. So how to align features or the input when we have 2D and 3D. So the problems are many LiDAR points may correspond to the same pixel because like they're just like different sensors, they're not at the same place. Maybe two LiDAR points are mapped in 2D to the same point. So how do we decide how we merge these? Or many pixels can correspond to the same LiDAR point. We know that LiDAR is more sparse, so input, but the image representation is very dense. So many points can correspond to many pixels can correspond to the same LiDAR point. Also, some measurements in one input may not be visible in the other one. So because they look from a different angle, they might not be the same exact point. Like we cannot find the area that is detected by the LiDAR in the image in many cases. There is also like movement and so forth. So this is definitely it's very hard to find a one-to-one mapping. And because the whole world is moving, like the geometry, linear algebra does not work perfectly. And one of the biggest challenges is, so data augmentation, as we know, is usually one of the best methods to just like increase the performance of our network a little bit, to just like give it just this some kind of invariance features. So we just like do, for example, in images, we do random crops, random flips, maybe rotations. In point clouds, we do other things such as like translations, rotations, and things like that. But usually we cannot, like they're not corresponding to each other. So we cannot apply the same transformation to the LiDAR and to the image. Because, for example, let's say we rotate the points in LiDAR in the, I don't know, around the Z dimension. We cannot do it in the images because rotating around the Z dimension would mean in camera to put the camera somewhere else, which we can definitely not do. So different augmentations make it significantly harder to perform this alignment task of multiple vision, multiple inputs. So much of a background. Let's go to what this DeepFusion does, and then just like put everything we have looked at that together to propose a solution, which is gonna be actually quite simple. So here we have a traditional, more traditional, let's say, method to fuse camera features and LiDAR features. So it just gets camera image and then extracts features, and then uses 3D geometry to map these into the LiDAR points, and then we use a LiDAR feature detector, LiDAR object detector to get the predictions. How can we do better? So we wanna extract features from both of them, and then somehow map these camera features into LiDAR features, and then use the LiDAR pipeline after this point. So what does this module correspond to? So here we see that we use our favorite attention here. So we have LiDAR features, which give us the queries for the attention, and the camera features, which gives us the key and values. So we just multiply query by the key, and then do softmax on it, and then just reweight the values to find which camera features correspond to this specific LiDAR feature. So we do a weighted sum, and then we do some fully convolutional, fully connected layers, and then concatenate the final result with the previous features from the LiDAR, and then we retrieve the fused feature. So they call this module layer neural align. So this is basically a attention, cross attention, LiDAR to camera cross attention layer, which is definitely like one of the ideas that many papers have. So let's see how this is utilized and what the results are. So they also do inverse augmentation. So here we don't see the inverse augmentation module, but we see a very useful image that enables us to understand what's going on. So on the A, on the first half figure, we have the original point cloud, and we do some augmentation on it before passing it to the neural network. So this is like default what all the methods do. And it gives us key points in the 3D coordinate system. And then this coordinate system is the augmented. So if we did rotation, the axis moved. So we have an augmented coordinate system. And if we want to move from this B directly to D, then we cannot directly project them because our view changed. So the points do not correspond to the correct places anymore. So this is not possible. What can be done is we just invert this augmentation, and then we just do geometry-based projection to project all the features, all the inputs to the 3D, to the 2D coordinate system. So this is basically what can be done. And what this inverse aug actually does is just after generating the LiDAR features, it keeps the augmentation that is done in the beginning, and just it inverts this augmentation in the feature level before doing the attention. So this is just, let me invert it so that the attention module can better align these features and then calculate the fused feature to use in the LiDAR detection part. So as probably most of you have noticed, this is extremely similar to the transfuser method that we observed. And there are a couple differences. So on the left-hand side, we have DeepFusion. On the right-hand side, we have transfuser from a couple of weeks ago. And so one of the major differences is that the left-hand side is a LiDAR point, like 3D oriented module, 3D oriented model. And on the right-hand side, we map everything to 2D and perform all the operations in 2D. So left-hand side moves everything to 3D, and right-hand side moves everything to the 2D. And then the right-hand side does this transformers in several layers, not only one layer. And on the left-hand side, we use attention in only one layer. So both use attention, right-hand side use transformers instead of just like basic attention. But these are very similar ideas. So this really shows that because both of these methods show state-of-the-art performance, this gives us a lot about how powerful attention is when it comes to the fusion of multiple modalities. All right, let's come to the experiments. So this is the main experiment, Waymo Open Dataset Challenge, and the task is a 3D object detection. So on the left-hand side, we have the test set, and on the right-hand side, we have the validation set. So for each method, they represent the average precision weighted by heading accuracy, and then average precision for level 2. So level 1 is easier, level 2 is the harder difficulty. And the blue ones, the blue lines show like single models in the benchmark. So this is the benchmark website. So the blue lines are single models and the white ones are ensembles. And we know that ensembles usually improve the performance of the model by quite a large margin usually. So ensemble is just having a couple models, maybe just like several models together and do some majority voting or just like averaging. So this DeepFusion ensemble is their ensemble method. So a couple models, majority voting, or just like average. And we see that it outperforms all the other methods in the Waymo Open Dataset Challenge test set. And they also observe that their single model, so non-ensemble model, is the best non-ensemble model in the challenge. So the other one, the next to it, is almost 2 points less in average precision level 1, for example. And it's the difference is similar in all the other methods, maybe even more. So DeepFusion significantly outperforms the previous models in the Waymo Open Dataset Challenge test set. And on the right-hand side, we see the results in the validation set. So there are two columns. One is vehicle prediction and one is pedestrian prediction. And we see that both DeepFusion and DeepFusion Ensemble, they're successful methods. They outperform the previous ones. So it's not so fair to compare DeepFusion Ensemble in this because the other methods are not ensembles, but the DeepFusion already outperforms all of them in some cases, especially by quite a large margin. So we can definitely say that this model, this idea worked really well. So we can also interpret DeepFusion as a plugin. So if you have a LiDAR-based object detection pipeline, we can just use DeepFusion as a LiDAR feature enhancer. So what it does is it also gets the camera features and then aligns them and concatenates them with the LiDAR features, which we see on the right-hand side, results in a consistent improvement in all of the three baselines, but also the improved versions of them. So even in the improved versions, we see that there is quite a large improvement just using DeepFusion as a plugin. So the fact that DeepFusion improves performance in all of the baselines definitely means that like this camera, this additional input is definitely bringing value. And this is not only just like one instance, this is not only one extremely well optimized, hyperparameter optimized model, but this is actually something that brings value to the LiDAR detection methods. So the authors thought like where the improvement comes from. So what is different in DeepFusion than other LiDAR detection methods? So they grouped the objects by their distance to the ego vehicle, and they see that the best improvement is in distant objects. So on the right-hand side, we see the figure. So we see for like three different groups, 0 to 30 meters, 30 to 50 meters, and 50 meters to infinity. We have level 1 and level 2 difficulties of single model and then multi-modal architectures. And we see that if the distance increases, then the difference between the performances increase also too. And they think that a possible reason for this might be that LiDAR gets even more sparse when distance increases. So this dense camera information has a great value, is quite important when for the distant objects where we have a very sparse LiDAR information, which definitely makes sense. So let's go to some ablation studies. So here we see the effect of inverse augmentation and learnable align on the model. So we see that if we use all of them, they just, in almost all cases, in almost all metrics, they improve the performance a lot. Especially we see that inverse augmentation is quite useful, and if they are both combined, we see even a greater increase in performance. So both of the models, both of the modules definitely bring a lot of value to the model. And they also compare different fusion models. So this is just like different methods that both use LiDAR and camera to do object prediction. So a single model which doesn't use camera at all. And then they have input fusion and late fusion. These are from like other baselines, and then deep fusion in the end. And then we see that deep fusion is the best one. So they see that using neural networks to align the features is the most successful way of fusing things. And we also see that latency is kind of comparable. So single model is like 0.16, and then all the other fusion methods are kind of comparable to deep fusion. We can see here, this is not like quite mentioned, but we can see here also that this model cannot work real time because it can only evaluate 3 images in every second. So we have 3 FPS, which is not ideal. So there is still a lot of room to increase the latency to use it in a real life scenario. So then here they just see the effect of multi-modal vision with regards to augmentation. So they get the inverse augmentation module out of the network and then do a couple trainings. And in these trainings, they change the amount of augmentation from, for example, rotation of 0 to the rotation of 15%, rotation of 30%, and rotation of 45%. And this is to understand what is the improvement of the multi-modal fusion when the augmentation amount changes. So they see that the improvement decreases when there is a large amount of augmentation. So the augmentation makes it hard to align these features, which degrades the performance of the multi-modal model. And this shows that the inverse augmentation model is very useful and is very important for this model, because we cannot use augmentations otherwise if we don't have the inverse augmentation model. So this is like an image. Then an example shows how inverse augmentation changes the alignment. On the left-hand side, we see that the alignment's almost good, but probably because of the random rotation, just the points are shifted by a small margin. So alignment is improved significantly when we do inverse augmentation. We can also try to see the effect of learnable align. So these are some attention maps for some pillars, some LiDAR pillars. So this is just a area of LiDAR. And then we see that these points, what are the pixels that these points are attending to. So we see on the first 2 images that LiDAR points attend to mostly head parts of the pedestrians, which actually makes sense because heads are quite important features, so to say, of a pedestrian. So they're quite useful in detection. On the right-hand side, we see that these pillars just attend to the borders of the image. And this is also very important, very sensible because then like our goal is to perform 3D object detection. So we want to know what the boundaries of the object are. So let's come to the last two experiments. So these experiments are on robustness. So we know that robustness is definitely one of the most important facts of any architecture. We want to see how we don't want to only have a look at the training data versus validation data and test data. We want to see how the input corruption or out of distribution inputs can decrease the performance of our model. So here we have a table. In this table, we have two sections. In the first section, we have a single model architecture, which only uses LiDAR. And if we add laser noise to the LiDAR, then we see that there is a 10-point decrease in performance on the right-hand side. So, but if we do deep fusion, if we use both modalities, and even if we apply pixel noise to the image and laser noise to the LiDAR, this decrease is still less than one point. So a possible reason for this is that sensors complement each other. If there is a noise in one sensor, the other sensor can make up for this weakness of the other sensor in that area, which helps getting more robust against any corruption in any of the areas, any of the sensors. And the next thing is out of distribution input. So out of distribution means that, so usually when we perform deep learning, one of the biggest assumptions we have is that in real life, which is our test case data set, test set, the distribution is going to be the same as in the training set. So we're just approximating the distribution of the training set, and we think that the test set is going to be the same. However, what if it changes? What if we get an out of distribution input? So they also check how the out of distribution input affects this. And then we see that multiple sensors help avoiding just overfitting. So it still overfits. So on the right-hand side, we see that the default input, default validation set, has a significantly larger APH, level 2 APH than Kirkland, which is not in the training set. However, the performance is quite bigger. From in the real validation set, the improvement is just 4 points from 6 to 3, but in the out of distribution test set, we see that the improvement is 7 points to 27 points, which is, I don't know, 25% increase. So this definitely helps us get more generalizable features, but there's still a way to go. And the last thing is latency versus accuracy. So we can make our model arbitrarily more complicated, but we always need to look back and see if we just added more complexity into the model, more computation power, and then is this the reason of the improvement, or just did we really introduce some important design change to the model, which resulted in a improved performance? And we see here that they just took LiDAR-only models and they scaled them up. So they improved they increased the size of the latent dimensions, they increased the size of detectors and everything, and then just they compared their accuracy to Deep Fusion, we see that Deep Fusion outperforms all of them. So even the more complex model, more computationally heavy model, and at the same latency, if the latency is 0.32, then Deep Fusion outperforms LiDAR-only model. So if we have the same budget, we wanna rather use 2 sensors rather than putting a lot of learnable parameters to the only LiDAR input. So as a summary, Deep Fusion proposes learnable align to utilize attention to align image and LiDAR features, and inverse augmentation to prevent alignment difficulties resulting from augmentation, and then their model results in the state-of-the-art performance in several benchmarks, most importantly, a very open data set. So I wanna quickly, just like very quickly mention our future work as section, not future, it's current and past work and future work too. This is self-supervised learning for multi-modal fusion. So RFA, Gabriel and me were inspired by the previous model that used transformers on autonomous driving. And then we wanted to use self-supervised learning for multi-modal fusion. So this is the model of the autonomous, like the previous autonomous driving architecture. We have RGB and LiDAR, we have like some encoders, and then we have like this transformer block where there is like encoders, decoders on the each side, and then there's multi-level transformers. So this is not like a transformer module. It's not like a simple transformer, but like feature extractor fused with transformers, and then we get the features, fused features. We pass them through MLP and GRU to get the waypoints, prediction waypoints. So we wanna add some self-supervision into this to improve the alignment. So what we wanna do is we wanna teach the network what points in the image correspond to what points in the LiDAR. So how can we do this? We can add some self-supervisory losses. So we can add a RGB to LiDAR decoder that gets the RGB encoder features before fusion and then predicts the LiDAR. And then the LiDAR decoder can predict LiDAR features from predict an RGB image out of the LiDAR encoder. And then we hope that these are gonna help these features that RGB encoder and LiDAR encoder retrieves to encode the information about correspondences between LiDAR input and RGB input. We also wanna put a next frame predictor, which is gonna give the network the supervision about future. So if we see a car in front of us, we wanna know where this car is going to. If this car is going away from us, then we don't wanna decrease our speed. But if the car is going like towards us, then we want to brake. So we want to put this next frame predictor after the fused features so that our fused features include the information about the predicted future state of the whole environment. And then we want to keep the MLP part the same and then apply this algorithm. So in the end, our final loss would be alpha times RGB to LiDAR loss, and then beta times LiDAR to RGB loss, and then gamma times next frame prediction loss and the original loss. So alpha, beta, gamma, these are hyperparameters. We still work on if we should use them only in the pre-training, or should they be still applied in during the training as well, or maybe should they be cut off in the middle of the training. These are all still the questions that we want to answer in this project. So an idea would be just use the same model as the other one and then just add a 3D object detector inside of it. So this would directly convert this model to like a 3D object detector model. So this can be also a future work for the model that we just have seen. So this also, because it also works on the alignment task, these self-supervisory losses can definitely help the model perform better. So this was all from my side, and then I am open to any questions from you. Thank you so much for listening to this long presentation.
Okay, so the topic is very impressive, and Barry covers both background knowledge and also some potential future works they're working right now. Any question from students on this paper?
Hi, Professor. I have a question.
Yeah, sure. Go ahead.
And in this paper, the author does not mention it's early fusion, middle fusion, or late fusion. So, so what do you think? Is middle or late, or just early fusion? I mean, because it has multi-modal, right? They combine the feature. So, yeah.
Yeah, this is actually kind of a late fusion. So late fusion, but we don't use geometry, but the learned features, we just do attention. So this is actually like a late fusion. So if we want to call the previous model, where did I put the, yeah, when we want to go through this previous model, this transfuser, then transfuser is definitely like, it's not, right, sorry. Where was it? I lost the, I deleted it. Interesting. I deleted the slide and I can find it. Okay, so yeah, definitely like the previous autonomous driving module is not late fusion, it's not early fusion, it performs fusion in several steps. However, this method can be considered as late fusion. It can also be considered mid fusion because like after the fusion, like we concatenate. So I would say it's a late fusion. And I actually thought, especially in the previous model as well, in this autonomous driving paper, that having so many like 4 levels of transformers is, I think, redundant. I don't think that this would be so necessary to apply, put a transformer 4 times. So this is also what we want to experiment with. We want to decrease the amount of transformers to just like 1 or 2, so that like so many transformers, like we don't see so much value of getting transformers. And then in the experiments, we also already saw that even just like concatenation of the features, no transformers, just the addition operator is already performing quite good in as the late fusion baseline that they represented. So adding 1 transformer is for us like enough. And I think that the late fusion with attention has enough potential to fuse all these features.
Okay, thank you.
Right. Thanks for the question.
Yeah, by the way, did it also mention how deep is the model? The only model has only one single layer of the transformer, right?
Yeah, this, which model you mean?
I mean, the model proposed in this paper, they only have one layer of this fusion for the transformer.
Yeah, exactly. I mean, it's not even like a transformer, it's just like one layer of attention.
Right, just one layer of attention mechanism for the updating one. Anyway, yeah, any more questions from students?
I have one question. Could you go to the slide where it talks about the latency or the delay between sort of the inferences?
All right. Here.
So when they've done this like latency check, is it like on an actual like GPU with like all these sort of like, I'm thinking like in an applied setting, when you have a self-driving car in the future, not every car is gonna come with like a, you know, really amazing GPU like attached to it. So like my question is like the performance and everything's good and all, but like they don't even talk about like in a previous paper, they talked about using Carla, which is like a simulated system to sort of see how like the car goes in like a simulated like system. They don't even do this in this paper. So like looking at this, the delay and like the lack of like a simulated environment, do you think like the results that we see in this paper are actually like, you know, performant, like, or like groundbreaking or any way? Because like you can always take out performance or improve performance in some way, but if you really can't apply it, then what's the point?
Yeah, exactly. So this is one of the points. I mean, I think the main contribution, like already this late fusion and input fusion model. So these are not experiments that the authors did. They're just results from other papers.
I see.
Even these two like are not good at latency, so they were not worrying about reducing latency but more interested in the accuracy. So their goal was just like, let's keep the latency around the same region or the same ball region and then try to increase the accuracy. But I definitely agree with you that in order to put these into real life, in order to use them in like in a car, then we definitely need to improve latency a lot. But I think that we can, I mean, it's like even the computers, like gaming computers have like pretty good GPUs. I definitely think that cars also can have GPUs, but like quite good GPUs, but still like going from like 3 frames per second to 30 or to 60 frames per second is not like is a long way. But there are so many things that we can utilize there. For example, like we are doing like object detection here. We are not doing object tracking. So the consequent, like if we have one prediction, we already know a lot about the next prediction, next frame, and then the frame after that. So there are so many things that can be utilized to increase the usage of such models in real life, because like it's easier to predict once you have a good prediction in the previous kind of previous frame, because like so many things don't move, or just like you know where they're gonna go. So there's so many things to optimize in the later stages.
I see. Yeah. Thank you so much.
Yeah, any more questions from the students?
Yeah, I have a further question. Because this one, it just use a RGB, and if we, it's an open question. If we have a depth, I mean, that's how further the object in the image. Do you think they'll be more accurate, or maybe benefits more, or even we don't need the LiDAR anymore? So what do you think?
Yeah, definitely. I definitely agree with it. I don't know if we can just like, so that this is one of the challenges. I think I don't know if there is a, like, to my knowledge, there is not a sensor that would directly get the depth information as a picture. So for each pixel that would get the depth prediction, but this is definitely like would be significantly helpful in 3D detection, because like if you just only concatenate RGB image with the depth, like one layer like depth information for all of the pixels, then like we have all the information that LiDAR gives us, and we also have the structure. So our main problem was, how do we use linear algebra to put everything from 3D to 2D? So this main problem would be resolved, and I think that would significantly improve the accuracy and then the performance of our networks. I think so. If you, for example, if you use Carla, because it's just a graphics engine, like it can provide us with this information. So I kind of worked with like depth information giving from Carla before. It's a very valuable information, and using depth usually increases like the depth map of the computer graphics. So it's just like one of the layers in the G buffer, if you have any experience with computer graphics. But just like from the G buffer, and it greatly improves the performance of the model when it uses depth information, but it's kind of cheating because we don't have the sensor available to us.
Yeah, thank you.
Yeah, so for this question, I have some follow-up comments. I mean, so before we mentioned we can have some RGB images with depth, right? Actually, this kind of RGB image with depth always comes from the combination of the camera image with the 3D, I mean, point cloud data actually. So by combining them together, then we can create this RGB image with depth. The main reason is because if we only use cameras, we can get the RGB, these values, right? However, there is no way to get the depth. We only can get the depth via the Lidar, this kind of sensor, right? To calculate the depth, how far away this kind of object is. So by combining them together, then we can create this RGB image with depth, right? So this is more like only fusion, right? By fusing the raw data together to create RGB image with depth, right? So this is another way for fusing this kind of two kinds of model data together, right? Yeah. Anyway, so another question for this paper from students. if there is no other question, then probably that's it for today's talk. And the talk is very good. I mean, Barry's helped us cover all the basic background knowledge already for handling the 3D images. Also, he helps us discuss about the models proposed in this paper and also the experiments, right? And he also shares with us some ideas they are working on the project and on the paper for this course as well. I think the project, the architecture is very impressive, and you try to combine the self-supervised learning into your model architecture for training this kinds of, models for the 3D object detection with self-driving, right? It's a very interesting project. And I would like to recommend you can continue to work on them, and then let's see what you can get, for the project. Yeah. So yeah, if there's no other question, then probably that's it for today. And let's thank the speaker. Thank you so much, Barry, for the talk.
Thank you so much. I think there's one more question, like someone, I think one question in chat.
Yeah, sure.
Yeah, I actually have a question about 3D representation in Deep Fusion. So as you said, like there is voxel representation and also another representation, but I have seen like the giraffe paper that they use some like neutral radiance field representation. So I'm wondering, like rather than only point cloud and voxels, would you think it would be possible like to use like neutral radiance fields or radiance fields as a representation in 3D vision in the future in these tasks, or how might be their drawbacks? Or
yeah, it's definitely like using different like future like 3D representations is actually one of the like most popular research areas. I think that like what you say is makes definitely sense. I also know that like they kind of want to improve this volumetric grids because like, for example, you can just like in a volumetric grid, we don't need to have the same input resolution in every space of the grid. So if we have a large area, we can just say that, okay, this large area is just a 1 like 0. And then we get finer when we are closer to the surface, but we are more sparse when we move out of it. So we can just like create this like tree structure where we refine if we have surface. If we don't refine, if all the points are just zeros, and then this, for example, significantly helps the memory, even if as the sparse convolutions, this has a negative effect on the performance, but it helps us just like store more complex object in the scenes. There are also so many different ways of combining like some point clouds or just like creating like hierarchical representations of the input, so that like we like in 3D, like 3D world is different than 2D world. So it's not, we cannot just put 3D world into a grid. So a hierarchy of objects is definitely one of the areas that people are working on. So I definitely think that there's quite a lot of potential in using different representations. Yeah, I agree.
okay, thank you so much.
Yeah, that's a good point. Before we have one paper on giraffe, which is for the 3D image generation. I think this idea can be combined with self-driving car. You can do some data augmentation by creating some artificial instances of 3D images, right? And then can help train the model much better, probably. It's an open question. I think, Johan, you can explore in this direction as well if you're interested in this area. Right.
Okay, sure. Because I think there are also a previous question asking about the GPU performance and the thing. So I think one thing the giraffe did is like they eliminated the RGB values. So only like using like vector, something like they call radiance field. So I think that might be also one of the representation here in a CV task, like in autonomous driving like Waymo. So like we don't really need to like care about RGB. We only care about like object detections, right? So I think it might be good to explore a little bit, I guess.
Yeah, sure. You can explore more, right, for this direction. If you have any
Yeah,
questions, we can discuss later. Yeah.
Okay, sure.
Yeah. Yeah, any more questions from the students on this work? It's cool. This work is a very interesting paper. Yeah, any more questions? If there is no question, then probably that's it for today. So thanks so much, Barry, for the talk and for the QA. Yeah, thanks so much. Yeah, and that's it for today's talk. Thanks a lot for everyone for your attention time.